Okay, so we're very happy to have Sebastián Barbieri here for our second talk of the mini-series. We'll be talking about the Lanford-Ruelle theorem for sofic groups.
All right, thank you, Christopher. It's an honor to talk again in the UT Groups on Dynamics seminar. This time I'm going to talk about something I call the Lanford-Ruelle theorem for sofic groups. This is joint work with Tom Meyerovitch from Ben Gurion. So I want to start with a very simple toy problem to motivate what I'm going to say afterwards. Let me consider n particles or balls, 1, 2, 3, up to n, which have some weights given by some function from 1 up to n to the reals. All right, so I have these little n balls, and each one of them has some real weight. It could be a negative weight, I don't care. And I'm going to ask something very simple. What's the probability distribution on these particles that maximizes the entropy plus the integral of the weight? So what I want to do is essentially find the probability distribution, which is as random as possible. So that's what why I'm plugging the entropy there. But I also want to give more probability to things that have more weight. So I want to balance these two things together. So what I want to do is to find the probability distribution that maximizes entropy plus the integral of the weight. That has an explicit expression. And if you're doing a calculus course, you can solve these using Lagrange multipliers and find out that their answer is Boltzmann's distribution. So the answer is that the probability of each ball is just proportional to the exponential of the weight. Okay, that's something really well known. And what I'm going to do today is essentially try to take this idea and bring it to symbolic dynamics. So let me just have this slide with the basic definitions. I'm going to consider a countable group gamma and a finite set alpha, A, which is the alphabet. And I'm going to consider the full shift with the prodiscrete topology. So I take all functions from gamma to A, and I give that just the product of the discrete topology on A. A subshift is just going to be a subset of this space, which is closed in this prodiscrete topology, and it's invariant under the translation action of the group. All right. And okay, given a finite subset of the group and a function from this finite subset to A, I call that a pattern. And given a pattern, I define the cylinder as the set of maps from gamma to A, such that restricted to F give me P. And my last definition is a subshift of finite type is a subshift that I can describe in the following way. There is a finite subset of the group and a finite set of patterns such that a configuration belongs in the subshift of finite type if and only if each of its translates lie in one of these allowed patterns. Okay, so this is probably for the people that are attending this talk, you've heard this several times. That's what I haven't stopped too much on these slides. If you want me to give more details, just let me know and I can slow down a little bit. So those are going to be the objects I'm going to be considering. I'm going to be considering subshifts and subshifts of finite type. And I'm going to want to generalize this idea of having Boltzmann distributions on them. So there's two ways to extend this kind of distribution to subshifts. There is a local way of thinking, which is the following. I fix a finite subset of the group, and I'm going to ask that the probability of seeing a pattern in those positions conditioned on the sigma algebra on the complement of F follows Boltzmann's distribution on allowable patterns. So every pattern that could go there, I look at them all, and I want them to follow Boltzmann's distribution. So that's going to be a local way of extending this notion into subshifts, and that's going to lead to a notion called Gibbs measure. There's another way of thinking, which is global. Instead of trying to create the Boltzmann distribution locally, I'm going to say, well, how did I get Boltzmann distribution in the first place? I was maximizing entropy plus integral of the weight. So I'm just going to say that the measure is an equilibrium measure if it maximizes the entropy of the dynamical system of the shift plus the integral of this function that I have from the shift to the reals. Okay, so I'm going to have these two notions. One is local, one is global. And the main question that I'm going to try to answer today is how are they related? Okay, if you're worried because I haven't defined any of these things, don't worry because I'm going to define them carefully later on. Okay, this is just the motivation for what comes next. All right, so what can I tell you what was done in the 70s or the 60s? I'm gonna look at a very restricted setting. I was looking at countable groups. Now I'm gonna just look at Z to the D. I'm gonna fix a subshift in A to the Z to the D. I'm gonna take a map from the subshift to the reals, which is regular enough. I will say at the end of the talk what regular enough means. And I'm gonna take an invariant measure, Borel invariant probability measure on X. And there are two theorems. One is a theorem by Lanford and Ruelle from 1969 that says that if X is a subshift of finite type, then equilibrium measures are automatically Gibbs. So these measures that you obtain by globally maximizing the topological entropy of the subshift plus the integral of the weight are automatically going to be locally, are going to follow Boltzmann's distribution locally. Okay, and that's what's called the Lanford-Ruelle theorem. On the other direction, there's a theorem by Dobrushin that says that if X is sufficiently mixing, and there's a particular condition that he gives, which he calls demixing, is then invariant Gibbs measures are automatically equilibrium measures. So these two notions are related and they depend upon different things. The first one depends upon a shadowing-like condition, like being a subshift of finite type, and the second one depends on mixing properties. Okay? All right, so these theorems were initially proven in Z to the D, and it's not hard to grab those proofs and generalize them immediately to amenable groups. What I'm gonna do today is I'm gonna try to go beyond and say what happens in sofic groups. So what we're gonna do is we're gonna present a version of this Lanford-Ruelle theorem on steroids. And what do I mean by steroids? First, I'm gonna replace Z to the D by an arbitrary sofic group. And second, I'm gonna take this condition that the subshift is a subshift of finite type, and I'm gonna replace it by a much weaker property, which is called the TMP or topological Markov property. It's much nicer in the sense that there are countably many subshifts of finite type, but there's actually uncountably many subshifts with the TMP for an arbitrary group. So it's a much more general property. And we're gonna see that this TMP property it's very related to Gibbsian-like properties in the space. Okay, so let me first state the theorem. My goal on this talk, or at least what I aim to do on the first 50 minutes of the 60-minute talk, is to explain the terms of this theorem. So the theorem goes as follows. I grab a sofic group. I'm going to grab a sofic approximation sequence for this group. I'm going to grab a function from a subshift in gamma, which is sufficiently regular. And then if this subshift has the topological Markov property and positive sofic topological entropy, then every equilibrium measure is going to be automatically Gibbs. That's the generalization of the Lanford-Ruelle theorem that we are asking for. So the only thing that is different from the first Lanford-Ruelle theorem beyond the generalizations that I asked before is that I need to ask that the system has positive topological entropy. That essentially means that the sofic approximation sequence can look at some invariant measure in a meaningful way. Okay? All right. So this is the plan for the talk. I'm going to try to explain the terms in this theorem on what remains.
Can I ask a question? So in Gibbs measure, you had a conditional measure.
Yes.
I'm not seeing that what you're conditioning on in this general thing. Presumably.
Oh, don't worry. I'm going to define Gibbs measures precisely in just a few slides.
Excellent.
So
Thank you.
don't worry. This was an introduction with moving events. Don't worry. I'm going to define all those things. So don't worry. You can ask me the question again if it wasn't clear later on. Okay, so my goal is to essentially explain the terms of this theorem and give you a very quick proof sketch. Before going into those details, though, I want to motivate this result. I don't really work in thermodynamical formalism. I'm more of a symbolic dynamics guy. And so I want to tell you one of the reasons I'm motivated into these kind of results. So a cellular automaton on the full shift is a continuous and gamma equivariant map from A to the gamma and to A to the gamma. Right, so I have my space A to the gamma, the full shift. I'm going to consider a continuous map which commutes with the translation action. And there is a very old and interesting conjecture still open, which is that for every group, every injective cellular automaton is automatically surjective. This is wide open. And it is known that sofic groups satisfy the conjecture. And well, it's not known whether all groups are sofics, and thus the conjecture is still open. Okay, we don't have any proof beyond sofic groups. So I want to motivate this Lanford-Ruelle theorem with the following application. Suppose I have not sofic entropy, but just an abstract entropy theory on the space of subshifts. What's that? I'm just going to have a map that maps a subshift and a measure supported on the subshift to a number in -infinity to infinity. Those two possibilities included. And I'm going to ask that that map is invariant under measurable dynamical isomorphism. So if I have two dynamical systems with measures that are measure theoretically isomorphic to each other, I want the value to be the same. Okay? I'm going to say that an abstract entropy theory, such as this, which is very simple, satisfies the Lanford-Ruelle theorem for the trivial function f, if for every measure that maximizes the entropy is a Gibbs measure. Okay, so for every measure on some subshift, I just can assign a number, and I'm gonna say that if every measure that maximizes this expression is automatically a Gibbs measure, then my entropy theory satisfies the Lanford-Ruelle theory. Okay, so my application is the following. If I have a group which admits an abstract entropy theory which satisfies Lanford-Ruelle theorem for f equals 0, then Gottschalk conjecture holds for that group. And the proof is very simple. Essentially, if I grab the full shift, it admits a unique Gibbs measure. That's something I'm going to prove later on. If I take the set of all configurations, there's a unique Gibbs measure, which is the uniform Bernoulli measure on the subshift, on the full shift. And it has full support. Now, if I have a proper subshift of a to the gamma, then the supremum of the entropies is going to be strictly less, because these measures have to be supported on X, and thus they cannot have the same value, because otherwise they would be Gibbs measures on the full shift, a Gibbs measure on the full shift, and then it would be the Bernoulli measure, right, which has full support. So I need to have that the supremum is strictly smaller. Then, if I have an injective endomorphism, for every measure mu on the full shift, well, the action of the group on this shift is isomorphic to the push forward, right? I have that this cellular automaton is injective, so well, the system is going to be isomorphic to its image. And well, if mu is the uniform Bernoulli measure, then this entropy, I know that it's the largest one, it's equal to this other one, and as every proper subsystem has a strictly smaller entropy, I need to have that this phi is surjective, right? So if for some reason I'm able to construct a very weird entropy theory and prove a Lanford-Ruelle theorem, which is very, very restricted just for the potential f equals 0, then I immediately have Gottschalk's conjecture. So it's some motivation, not a very good motivation, because I'm actually just proving it for sofic groups where the conjecture is already settled, but it's something that might be interesting to think on. Okay, so that's my motivation for the Lanford-Ruelle theorem. Now I'm going to try to define the terms equilibrium measure and Gibbs measure, and I want to start with Gibbs measures. So let me recall what I tried to tell you was the intuition behind Gibbs measures. A measure is going to be Gibbs if it locally follows Boltzmann's distribution. What does that mean? I fix a finite set. The inner rectangle that you see there, that's going to be my finite set. And imagine that green is just everything else. It's infinite. Here you just see a finite portion, but green is actually infinite. And what I would like is the following. If I look at any pattern that might appear there, for instance, that beautiful pattern, or that one, I would like that the conditional probability, mu of seeing one pattern condition on what I see outside, and mu of the other pattern condition on what I see outside, follow Boltzmann's distribution for some potential. Now, let me make that precise. I'm going to say that two configurations in the full shift are asymptotic, if they differ just in a finite set of coordinates. So if x restricted to the whole group minus this finite set coincides with y restricted to the whole group minus this finite set. So that 2 points are asymptotic. And I'm going to denote by T of x the equivalence relation of asymptotic pairs. Now, given a function from x to the reals, such that for every asymptotic pair, if I sum the difference of f in all translates of y, and I subtract the difference of f on all translates of x, and this gives me an absolute convergence series, well, I'm just going to consider f, and I'm going to construct this object, right? This object is going to be a cocycle, right, on the equivalence relation of asymptotic pairs. And well, if you are worried that this might be hard that this is absolutely convergent, just think on a function which is local, that depends on finitely many coordinates. If f is a function which depends on finitely many coordinates, then, well, if x and y are asymptotic, they differ just in finitely many places. So this sum above is just going to have finitely many non-zero terms, right? So that's going to be absolutely convergent. Okay, so I'm just going to consider functions f that satisfy this property. All right, so now I can define Gibbs measure. I fix a subject. For a given configuration and a finite subset of the group, I'm going to consider LF as the set of patterns which support F, such that if I concatenate them with X outside of F, they give me a proper element of X, right? I have a subshift, so there's no reason why if I grab some configuration, I erase F, and I plug in something, there's no reason why that should lay on X. I'm just going to denote by LF of X the patterns that stay there. So this is the definition, and that's why I didn't give it on the first place. It's a little bit complicated. A Borel probability measure mu in a subshift X is going to be Gibbs with respect to a function f for which a cocycle that can be defined. If for every finite subset and for every pattern in A to df, then mu almost everywhere, I have that the conditional expectation of seeing the pattern P conditioned on the sigma algebra outside of F, evaluated on X, follows Boltzmann's distribution, where the thing that I'm plugging in is this cocycle F. What is this thing? I have Boltzmann distribution, exponential of something divided by sum of exponentials. So I just need to tell you what's this something. This something is the cocycle that I gave you before, and I'm having two things, sorry. First, I'm going to have the original configuration X, and second, I'm going to have the configuration X where I erased the positions in F, and I plugged in the pattern P. So essentially, I'm comparing what's the transfer of energy if I erase the positions in F and I plug in P, right? I'm summing all over the translations of the group, so I'm just testing with F how much am I gaining or losing by doing that, right? So that's going to be kind of the energy contribution of this pattern here, conditional on X. And then I'm just going to take the Boltzmann distribution and say that and declare that that's a Gibbs measure. Okay, as I'm working on a subshift, this is well defined if P is allowable. So if I plug in P, this lies on X, and if not, I'm just gonna define that as 0. Okay, so that's my definition of Gibbs measure. Now, that's a little bit complicated, so let me give you a very, very simple example. Suppose I have the full shift. That's my favorite subshift. I just take the full shift, and I take F equals 0. Okay, so I need to tell you what would be this conditional distribution for a Gibbs measure. The conditional expectation of seeing a pattern P conditioned on the sigma algebra on X, well, it's this thing by definition. But then again, for the full shift, I have that every pattern I can paste it on X. So I don't have to take these if P lies there, if P lies there. I can just write the expression above. Second, as F is 0, the cocycle is going to be 0. So this exponential above is just the number 1. And this exponential below is just the number of terms that I'm summing. So this thing simplifies just to 1 over the size of the number of patterns which support F. And as you can see, this doesn't depend on X. So actually, the only Gibbs measure for the full shift is the uniform Bernoulli measure, which is what I told you before. Okay. Everything all right with respect to Gibbs measures?
So when you change X, you change the surroundings. And so these things can change with X.
Right, so the cocycle changes. I'm looking at, essentially I'm looking at asymptotic configurations where the asymptotic part is X outside of F, but the function F might depend on X.
Yes.
I mentioned local functions, but actually I'm going to be considering functions which are not local later on. So they might depend on all coordinates of X at once.
Right. So, but presumably the variation goes down a lot.
Yeah.
Okay.
I'm going to ask for either some variation or some very strong decay condition.
Okay.
Could you
remind the moment actually for most of this talk, we could think that F just depends on a finite number of coordinates, just to make the argument simpler. All right, so that's going to be a Gibbs measure for me. Later on, I'm going to give another characterization which I like much better. All right, so those are Gibbs measures. Now I need to tell you what equilibrium measures are. And I gave a definition. It's just something that maximizes entropy plus integral of the weight, but I need to tell you what entropy is. So if I fix a finite subset of a group and I take a subshift, I can define, similar as I did before, LF of X, but now as the set of patterns that appear in some configuration in X. Right? So there is some configuration where P appears at position F. And well, for Z to the D, there is a very simple formula for the entropy. The measured theoretical entropy of the translational action on a subshift is just going to be the limit of, well, I take the box of size of radius n on the, I don't know, infinity norm, and I just sum the Shannon entropy of the partition induced by all allowable patterns in this support. Right, and well, that is a well-defined number, which is called the measured theoretical entropy of a subshift. And an equilibrium measure is just going to be an invariant Borel probability measure, which maximizes this entropy plus the integral of the weight F. Right, here I can take F to be any continuous function or whatever, any integrable function. Okay, so it's very simple to define equilibrium measure, but then again, I'm just on Z to the D. So I wanted to state my theorem for sofic groups, so I need to go further. Just before that, let me just give an example, a very simple example. If I take Z to the D, I take the full shift, and I take the function 0, well, this ugly expression is just maximized on, well, I take mu to be the uniform measure. So actually, the only equilibrium measure for the zero potential is the uniform Bernoulli measure. And as you can see, this subshift, well, the full shift satisfies, it's very mixing, and it is a subshift of finite type. So it satisfies these two conditions that I mentioned before, the Bruchian and Lanford-Ruelle. So equilibriums and Gibbs measures coincide on A to the Z to the D, for F is equals to 0. Okay, not surprising. All right, so what to do if the group is not set to the D? As I mentioned before, there is a large class of groups where you can define entropy theory almost in the same way as set to the D, and those are amenable groups. So I'm going to define those groups right now. If I grab a finite subset of gamma and I grab a positive delta, I'm going to say that a subset of a group is K delta invariant. If after I shift it on the left by K and I take the difference, the symmetric difference with F, this is very small with respect to F. So it's smaller or equal than delta times the cardinality of F. This is the image. So imagine, for instance, here my group is Z squared. I take as K just the diagonal translation 1, 1, and I take a box of size n. Then, well, you could think that F is just the red square, KF is just the blue square, and then the symmetric difference is that thing that I have on the border. And if n is large enough, you can see that this is very small with respect to the cardinality of F, right? Okay, so I'm going to say that the group is amenable if for every K and every delta, I can find a set which is K delta invariant. Okay, so I can find sets which are as invariant as I want. I'm going to say that the sequence of finite subsets is failure if it is eventually k delta invariant for every k and for every delta. Okay, and well, if I have a Fellner sequence, I can define measured theoretical entropy in the same way as for Z to the D, except that instead of taking the balls of radius n, I'm just gonna take a Fellner sequence. So I'm gonna take the limit of 1 over the size of a Fellner sequence, and I'm gonna sum the Shannon entropy of the allowable patterns which support that Fellner sequence. And this limit does not depend on the Fellner sequence. It's well defined. Actually, it coincides with the infimum of that expression over all finite sets of the group, finite subsets. Okay. All right. So for amenable groups, I have these, and of course, I can define equilibrium measures in the same way as I did before. But what if gamma is not amenable? Now I'm running into problems. So entropy theory on amenable groups is quite nice because it satisfies two very beautiful properties. One is that if I have a factor map, then entropy does not increase. Second, the entropy of the full shift is log of the size of A. That's just a simple computation. Well, there is a very famous evil example by Ornstein and Weiss, which says that if I take the free group on two generators AB, which looks like that infinite quaternary tree, then I can find a factor from the two shift onto the four shift, which is like this. I just consider the two shift with alphabet, the cyclic group on two elements. I take the four shift and I think of the alphabet as the Klein group. And I define the map from the first to the second, where I just define phi of x on a position G on the free group as the coordinate at that position plus the coordinate on the right. And the second coordinate is going to be the x in G plus its neighbor on the north. Okay, you can verify it. It's quite easy to see that that's continuous and gamma equivariant, but that's actually surjective as well. It's not hard to show that it's surjective. Just fix a coordinate in the origin 0, and whenever you try to construct an image, you always have two choices, so you can always choose whatever you want. So, well, you can construct a factor map from the two shift to the four shift, and that means that either you keep the second property, so the entropy of the full shift is log of the size of the alphabet, and the first property fails, so entropy can increase under factors, or maybe you get the first property, but the second cannot hold. So you have to take a choice, right? You cannot have both properties on non-amenable groups, such as this one. Okay, so what do we do? There's a class of groups called sofic groups, which generalizes simultaneously the class of amenable groups and residually finite groups. And for that class of groups, there is a very nice, well-defined notion of entropy that was defined by Lewis Bowen. So let me try to give some intuition on what these sofic groups are. I'm going to give the definition, and then I'm going to tell you what this represents. Group gamma is sofic if I can find a sequence of finite sets whose size is growing to infinity, and a collection of maps from the group gamma to the symmetric group of this finite set, which is asymptotically an action and asymptotically free. So what I want to think is that these sigma i's, I want to think of them as almost representations, right? If, for instance, if I were able to make these sigma i's be homomorphisms, then my group gamma would be residually finite. And well, if I have the second property that it maps things non-trivially. My idea is the following. I'm going to think of these VIs as finite models. I don't have access to my whole group gamma. I just have this finite set of nodes. And I'm going to try to represent gamma faithfully by just making it act on this finite set of nodes. And I want this thing to look like an action. So I'm not going to ask that these maps sigma I are homomorphisms. I'm just going to ask that they are asymptotically an action. That means that if I take the limit as I goes to infinity, the number of vertices such that if I consider the permutation induced by ST on some vertex, and I consider the permutation induced by S and the one by T, and I compose them, then it gives me the same, that proportion approaches 1. So I'm going to ask that it is asymptotically like an action. And well, that wouldn't be enough, because I could take the trivial representation that sends everything to the identity in the symmetric group. So I'm also going to ask that this is free, so that things are actually moved, right? So the vertices such that they are distinguished by some position in the permutations are distinct for most of the vertices. Okay, so it's essentially a way of representing my group in a very, very, very general, weak way. Okay, so just a few examples to see how these generalize residually finite groups and amenable groups. If I have a residually finite group, by definition, there is a sequence of normal subgroups with finite index and whose intersection is trivial. That's one of the many equivalent characterizations of being a residually finite group. Well, I could take Bn as just the quotient of gamma over Hn, as Hn has finite index. This is a finite group. And I can take this map sigma n as just, well, left translation. This is well defined because this thing is a finite group. So this is very nice. This collection is not actually asymptotically an action. It's just an action. Point, right? It's just an action. And it is asymptotically free because the intersection of all these normal groups is trivial. So eventually, everyone is going to get into this finite set. Everyone's going to get represented non-trivial. Right? So this is a way of thinking, well, sofic groups generalize these residually finite groups in this very nice way. I'm not asking that this thing is an action. I'm actually just asking that it is asymptotically an action. Okay? And I also said that it generalizes amenable groups. So let me tell you why. If gamma is amenable, I can take a Fellner sequence, which contains the identity and grows up to the whole group. I can take my sequence of finite sets as my Fellner sequence, and I can define my functions sigma n in the following way. It's just translation by G, left translation by G, right? I'm going to define it as left translation by G if it lies inside my set Fn, and if it does not, well, I just apply some permutation of whatever remains. Okay, so this collection is going to be asymptotically an action, essentially because Fn is a Fellner sequence. So the number of Fs such that this thing lies outside is going to be very small asymptotically. And second, this is going to be asymptotically free because my set is growing up to the whole group. So everybody's going to be inside at some point and going to be moved non-trivially. Okay, so this shows that amenable groups are sofic. So this class is very nice. It generalizes these two well-known classes. So it's nice to have some entropy theory there. Okay, so this is the slide that I'm very afraid of. How to define sofic entropy for an action. And I'm afraid because the formula at first glance is hideous. After you look at it a while, you start to love it a lot, and I actually really enjoy the formula right now. But the first time that I saw this formula, it was painful to see. It looks like that. So you fix a sofic approximation sequence of your sofic group, and you take a generating pseudometric on your space. And well, sofic entropy is exactly that formula. It's a supremum over epsilon, and you take infimum over three different things: finite subsets of continuous functions on X, finite subsets of the group, deltas. You take the lim sup as I go to infinity of 1 over bi log of something, where something is the maximum ordinality of a collection of maps from these finite sets Vn up to X, such that they are separated in the sense of the Rufus-Bowen metric. They are very close to an orbit, parameterized by this function f and delta. And they are almost generic with respect to the measure, in the sense that if I take like this Virchow average, well, it's the same as integrating h for every h in this finite subset of continuous functions. So essentially what I'm saying here is I'm taking Rufus-Bowen's definition of entropy through separated sets, and instead of considering orbits, I'm considering separated almost orbits or pseudo-orbits. And you can show that in amenable group theory, that gives you the same entropy that you're all used to work with. And well, in this case, it makes a lot of sense. This was defined by Lewis-Bowen. Not exact, well, yeah, essentially in the same way, I think. Okay, there are many details here, but this is too general. This is for a general action of gamma over a compact set. For a subshift, this thing is much simpler. So, okay, I can simplify things a little bit. What if I have just a subshift? First things first, subshifts are expansive actions. So epsilon, I don't care, I can replace it by a half. So, okay, the formula is a little bit simpler now. I don't have this supremum over epsilon. Okay, that's nice. Second thing, I always took a generating pseudometric, but for subshifts, there's a very nice, simple generating pseudometric. Just compare the coordinate at the origin, right? So, okay, that should simplify things a little bit. And also, I don't need to really look at maps from BI to the whole space. This thing is expansive, so I can just look at the zero coordinate through this pseudometric. So if I have just a map from BI to the alphabet A, I can push forward this finite coloring to a configuration gamma by using the map sigma I. I just fix a vertex, and from that vertex, I start acting by sigma I of G. And that gives me a configuration. There's no reason why that should be on the space, but it gives me some configuration on the full sheet. And each one of these configurations induces a probability measure. Well, how so? I take W, this induces configurations, and then I just sum the deltas over these configurations. Right, so that induces a probability measure. It's not invariant. It's far from invariant. It's just a probability measure. But the good thing is that using this probability measure, I can reparameterize what was reading on the sofic entropy. Well, again, I have the sofic approximation sequence. I take now a metric on the space of probability measures for A to the gamma. I don't know the Cantor-Wiesbass-Einstein distance. And I'm going to define for a probability measure, an invariant probability measure on X, I'm going to define n delta of mu as the set of probability measures on the full shift, which are close. Okay, just a ball around mu. And it turns out that I can write the sofic entropy of a subshift with respect to a sofic approximation sequence in this much simpler way. I just take the infimum over delta of the lim sup of 1 over vi of the logarithm of the number of maps from my finite model vi to A, such that the measure induced by this W is in the delta neighborhood of the invariant measure I'm considering on my subshift. So if I write things this way, it's nice because I can parameterize everything that was written before with a single parameter delta. Of course, it's not so clear to see what this delta neighborhood is, and I'm hiding a lot of things, but for some purposes, it's easier to work in this way. Okay, so it's just a simpler way of presenting sofic entropy, and I think it's as simple as I can get. So okay, now that I have this definition, I'm going to say that an invariant Borel probability measure is an equilibrium measure for a subshift with respect to a sofic approximation sequence and a function if it maximizes the sofic entropy plus the integral of the function. Okay, so after all this work is done, I managed to define the equilibrium measures for subshifts on sofic groups. Sorry if this was too long. All right, so let me go back to the theorem. I have a sofic group, I have a sofic approximation sequence, I have a function which is sufficiently regular. I'm claiming that every subshift which has some mysterious property called TMP and positive topological sofic entropy, which I haven't defined, then every equilibrium measure is Gibbs. So the things that are marked in blue I have defined. I've told you what a sofic group is. I've told you what an equilibrium measure is. I've told you what Gibbs is. I need to define 3 more things. What does it mean to be sufficiently regular? What does it mean to have TMP? And what does it mean to have positive topological entropy? The third one is easy. I can cheat and use the variational principle, which I'm not going to tell you anything about. And I can say that the topological sofic entropy is positive if and only if there is an invariant Borel probability measure with non-negative sofic topological, non-negative sofic measure theoretical entropy. Okay, so that's cheating, but that's the same thing. So that's defined. So I just need to tell you what TMP means and what sufficiently regular means. And TMP is something quite interesting. All right, you can forget everything that I said before. I'm gonna grab a closed set on the full shift, not necessarily invariant. And I'm gonna say that this set satisfies the topological Markov property if for every finite subset of the group, there is another finite subset, which I call the memory set, M, which contains S, such that for every pair of configurations, X and Y, such that they coincide in the memory set, but not S. So here I have these two configurations, X and Y. They are anything, but they happen to coincide in this region M minus S. They have exactly the same symbols. Every time I have two configurations like this, I can paste both of them inside of S and outside of M. So then I can grab what is in X in S, put it there. I can grab what is on Y outside of M, put it there. And the resulting configuration will be on the subshift, on X. Okay, so it's like a very, very weak pasting property. For every finite set, there is a bigger set such that if I coincide on this boundary, then I can paste what's outside with what's inside. Okay? All right. So it's not hard to see that subshifts of finite type automatically have this topological Markov property. Actually, you could think of subshifts of finite type as systems that have shadowing, and TMP is just a very, very, very weak form of shadowing. It just says that if I have two orbits which coincide in a very particular region, then I can paste part of one with part of the other. So SFTs are much, much stronger than that. They have the pseudo-orbit tracing property. Okay, so in the spirit of this TMP thing that I just defined, I'm going to say the following thing. I'm going to say that two patterns with support F are exchangeable in a subshift if each time that I can grab some configuration, erase the coordinates at F and put P and obtain something in X, then I can erase P, put Q, and I obtain something in X. So essentially it means that whenever I see P, I can erase it, put Q, and I don't leave my subshift. Okay, so that's going to be an exchangeable pair of patterns. And the interesting remark is that if I have that X has the topological Markov property and M is a memory set for some finite set F, then for each pair of configurations which coincide outside of F, then X restricted to M and Y restricted to M are exchangeable, right? Just because I have the topological Markov property, right? I coincide in M minus S, so I'm going to be able to exchange these two patterns whenever I see them. All right, and well, I am a subshift, so I'm translation invariant, so the former property actually becomes invariant under translations. All right, so let me remind you that I denoted by T of X the equivalence relation of asymptotic pairs. Now, if I just consider exchangeable patterns, I can define a subrelation of the asymptotic relation, which is the one that is induced by exchangeable patterns. And I'm going to call it the étal asymptotic relation. Here's an example. I'm going to consider the sunny side up subshift. The sunny side up subshift is just a set of all maps from Z to 0, 1, where I see at most one coordinate with a 1. So something like that. I could see no ones at all, or just 1, 1 at some position. Okay? If I look at the asymptotic relation, well, at most, two configurations can at most differ on 2 coordinates. So everything's going to be asymptotic to everything. So the asymptotic relation is the product of the shift with itself. But the étal asymptotic relation is actually the diagonal. Why? Because I cannot exchange patterns. If I have any two patterns, which are different, well, one must have a 1 somewhere, and I can definitely not exchange it by another one because I could create problems. Right? I could create more than 1, 1 in some configuration. So, okay, this is an example. And there's a theorem we proved that says that these two relations coincide if and only if the space has the topological Markov property. Okay, so it's a characterization of the topological Markov property in terms of these two equivalence relations. So Okay, I just copied and pasted here the definition of Gibbs measure because I'm going to give a slightly different definition of Gibbs measure, which is equivalent. If you look at that expression above, and I take two patterns that are compatible with X, well, I can just divide these conditional expectations. And the exactly denominator is going to cancel out. And what I have is, well, exponential of the cocycle divided by exponential of the cocycle. I put those together. I use the fact that this is a cocycle. And I can actually just compare Q with X outside and P with X outside with the cocycle. So that's a nicer expression. And now if I do the following, I take a measure which is non-singular with respect to a countable equivalence relation, such as the asymptotic relation. And for such an equivalence relation, I can find a countable group which generates the relation, and the map, which is a collection of the all Radon-Nikodym derivatives for the elements in this group. So, for instance, for the asymptotic relation, I can construct a countable group that induces this equivalence relation as the orbit relation. And for each one of these maps, I can consider the Radon-Nikodym derivative of du composed with phi with respect to du, and wrap them all into one big cocycle, which is defined almost everywhere. Well, with some work, I can show that I can redefine what it means to be a Gibbs measure by saying that this Radon-Nikodym cocycle is exactly the exponential of the cocycle, mu almost everywhere. And the interesting thing is that, well, now that I have defined defined Gibbsianness in terms of an equivalence relation, I can define a weaker notion, which is étal Gibbs, if this just happens with respect to the étal equivalence relation, this one induced by exchangeable patterns. Okay, so this is just another way of saying things. But the interesting thing is that if a subshift has the topological Markov property, then these two equivalence relations coincide, and thus this definition of étal Gibbs that I gave coincides with Gibbs. So what I'm actually going to prove is the following. This is the real theorem we proved. We didn't prove things for subshifts with TMP. We proved a Lanford-Ruelle theorem for all subshifts with no condition whatsoever, but with a weaker conclusion. We conclude that every equilibrium measure is always étal Gibbs. So it is going to be Gibbs with respect to this weaker equivalence relation. And in the case where the subshift has the TMP, for instance, a subshift of finite type, well, I'm going to get the usual Gibbs condition at the end. Okay, so what I'm actually going to do in my proof is not consider the condition, the topological Markov property, but I'm just going to try to prove Gibbsianness for this for the smaller equivalence relation, the one generated by exchangeable patterns. Okay, so that's actually one of the main techniques we use on this proof. So, okay, just again, the example of the sunny side up. This subshift contains a unique invariant measure, which is the delta mass on the uniform configuration. And so this is the equilibrium measure for any sofic group and every sofic approximation sequence. So it has sofic entropy 0. It's very boring. This measure is, of course, not Gibbs because it's going to be singular with respect to this asymptotic equivalence relation. But it is trivially étal Gibbs because the étal equivalence relation is trivial. Right, so the theorem holds. It holds trivially. It's very boring, but okay. In this subshift which does not satisfy the topological Markov property, I get this weaker condition that the measure is étal Gibbs. Okay. All right, so I want to give you a very, very quick proof sketch. I'm going to hide a lot of details, but I just want to give you the main ideas that are hidden in this proof. The first is that I'm going to do the proof for a local map, which is going to suppose that f depends on finitely many coordinates. Then what I do is the following. I'm going to grab an asymptotic pair in the étal asymptotic relation and a finite subset such that the patterns x restricted to f and y restricted to f do not overlap and are exchangeable, right? These x and y live in the étal asymptotic relation, so for big enough f, these guys are exchangeable, and I am going to suppose that they do not overlap. What does that mean? That if I put them, I cannot see them on a configuration on the full shift overlapping somewhere. It's not exactly that. It's a slightly weaker condition, but it's really technical. The idea is essentially that if I were to replace occurrences of the pattern P by the pattern Q, I would not create any newer occurrences of the pattern P. So there is a unique way to erase and replace. Okay? It's just going to be a very technical condition. And then what I'm going to do is I'm going to consider the set of measures, mu, such that the measure of seeing P or Q is close to a number T, and the ratio between the measures, the probability of seeing these patterns, P and Q, is close to a number R. So I'm just going to parameterize those two things, right? I'm going to control the probability of seeing these patterns, any of those, and how do they compare. And what we can show just by doing horrible computations is that if I take two different ratios, R and S, then the difference on the expressions for sofic pressure that appeared on the sofic entropy, well, it's a little bit more complicated, they can be parameterized by an expression like the one I wrote there. It's T, the probability of seeing P and Q, and then I can, well, more or less say what the difference between the pressures induced by these ratios are by taking the entropies of these values R and S that I define there, and then multiplying these values by the cocycle between X and Y. Okay, so essentially I move to a very, 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 very local space. I try to replace occurrences of X, Y, Y, and I try to see how that changes the topological, the sofic pressure. And I can exactly compute how it's gonna differ when I move these terms. Okay, so what's the point? In this expression below, if T is non-trivial, that means if these patterns P and Q actually appear in the support of the measure, then the maximum value for this pressure is going to be obtained where the ratio is exactly the one that I'm looking for, the exponential of the cocycle, the Gibbs thing. So that's essentially the whole core of the proof. We take patterns that do not overlap, we do some replacing, we do horrible computations, and we end up showing that we can describe how the pressures would be modified by changing the ratio between two patterns. So essentially the idea is that if these patterns are going to maximize the sofic pressure, then they should have this ratio. So, okay, after I have that, if I have any two étale asymptotic configurations which satisfy this overlapping technical condition and are in the support of an equilibrium measure, I'm going to be able to show that the limit of these measures, the pattern X restricted to F and Y restricted to F as F goes to infinity, is going to be exactly the one on the Radon-Nikodym cocycle. So this is going to imply that the equilibrium measure is Gibbs. So that part of the proof is not that hard. What is really hard afterwards is getting rid of the technical condition. So this uses some somewhat standard techniques. Essentially what we do is we take the product with a Bernoulli shift and we show that the non-overlap condition is generic on a Bernoulli shift. So that involves a lot of Borel-Cantelli and computing stuff. All right, but that's just technical. Essentially, that's the core of the proof for local functions. And then, well, if we want to do it for non-local functions, we do that through functional analysis by looking at equilibrium measures as subderivatives and using some sort of Mazur-like theorem. Okay, so that's not really that different from what was done on the papers on the 60s. It's slightly more complicated, but not that different in spirit. Okay, so I think I've explained most of the terms on the theorem, except that I said that this works for sufficiently regular functions. And of course, I'm not going to be happy just with local functions. So let me tell you about two spaces of functions where this works, which are quite classical. The first are interactions. So I can say that the translation invariant map from the language of a subshift to the reals is an interaction. I'm going to say that this map is absolutely summable. If I sum over all finite subsets of the group which contain the identity, and I take the supremum of this function over all patterns which support F, this thing is finite. So it's a very, very strong condition saying that these values are not wildly growing, they decrease very fast. And given an interaction like that, I can define a function from x to r just by summing over all finite subsets that contain the identity and dividing by their set, by their size. Okay. Well, these maps that are generated by an absolutely summable interaction, they all satisfy the Lanford-Ruelle theorem. Okay, so if you have done thermodynamical formalism and you are used to working with interactions or absolutely summable interactions, the theorem works for them. So you can be happy about that. The second is related to what Doug said. If I take now a finite sequence of subsets of a group that grow up to the group, I'm going to call it a filtration. I can take a function and a finite subset of gamma, and I can define the variation over this finite subset as well, the variation, the supremum of the differences for x, y, and x that coincide in this set. And I can say that the map has f-summable variation if whenever I sum these variations over these larger and larger sets, and I put as a constant the growth of this sequence with respect to S, this is finite. Okay, so I'm gonna say that the map has f-summable variation if this sum for every finite subset S is finite. It's a somewhat strong condition. It coincides with the usual summable variation conditions on Z to the D. Well, I can prove that for anything of this sort, anything like this, these maps satisfy the LR theorem as well. So if you like these kind of maps, you can also use them. All right, and just to finish, I just want to tell you a few applications of the result. Let us assume that I have a setting where the conditions of the LR theorem hold. The first one is quite trivial. If there is a measure such that the sofic measure theoretical entropy is non-negative for some sofic approximation sequence, then there are actually Gibbs measures on my system. It's quite obvious. Equilibrium measures under the Lanford-Ruelle theorem are Gibbs measures. So if there is one, well, there is also a Gibbs measure. Kind of boring, but not at all that obvious without the LR theorem. Second, and this one is, I think, much more interesting. There are some ways of showing that some systems admit unique Gibbs measures. For instance, I showed that the full shift admits a unique Gibbs measure. Well, if there is a unique Gibbs measure and the sofic topological entropy is non-negative, then the equilibrium measure must be unique because they must coincide with this unique Gibbs measure. And it will not depend upon the sofic approximation sequence. So that's interesting, especially because there is a paper by Lewis Bowen and some other people where they constructed examples of a subshift of finite type, I think it's strongly reducible, which with two different sofic approximation sequences can take two different positive values of sofic topological entropy. And I think the question is open for measurable sofic entropy. Well, if somehow you could construct an example which has a unique Gibbs measure, you could use that to solve that, to give an example where you have two different measure theoretical sofic entropies which differ with different sofic approximation sequence. Yeah. So we tried doing that. We didn't manage. So okay, that's the application we're writing. And the third one is actually quite interesting. I like it. Suppose now that my alphabet is a finite group and that I have a subshift which is closed under pointwise multiplication. Well, I can show that all these subshifts automatically satisfy the topological Markov property. This is for free. Actually, it's free for any algebraic action. And if this homoclinic group, which is just the set of points in my subshift which are homoclinic to the identity, is dense, then I can show that the hard measure on this group is the unique measure of maximal entropy for every sofic approximation sequence. So it's a kind of cute, straightforward application of the LR theorem.
That's true for any sofic group, gamma?
Yeah, sofic group, for any sofic group.
And soficness is essential to assume?
Well, we're using the LR theorem to prove it, so... No, I don't know. Maybe you can prove this for general groups. I have no idea without the LR theorem. But it's just that with the theorem we prove, this is just a straightforward application. And that's all, folks.
Thanks.
Thank you.